Hello everyone and welcome back to the online NPTEL certification course on aquatic geochemistry. We have been discussing previously some of the global water challenges, and then we discussed about some of the future visions and solutions, and the hydrological cycle, the global hydrological cycle. And in this particular lecture we will be discussing about the catchment hydrology, right. So, moving on to basic concepts of hydrology. Now, when we talk about any problem, then we have to make it sizable such that a solution can be prescribed, right. So, when we are looking into a system in hydrology, we talk in terms of a catchment or a watershed. Okay. So, especially for terrestrial systems. Okay. So, say for a river, a lake or the groundwater, we always talk about what is happening in that particular catchment, because if it is too broad, we can't control it. There will be so many parameters that will be you will not know which one is causing the problem, which one to control. So, where to place your solution, right. So, for a sizable volume to get a control volume, that control volume is our watershed. So, in hydrology, our first thing that we try to understand is what is a watershed. Okay. Now, in terms of rivers, it is also called as the drainage basin or the river basin or a catchment. Now, same thing can be applied for a groundwater system also, for a lake also. So, whatever is the area or the topography that feeds water into that particular aquatic system is its watershed or catchment. Okay. So, the watershed is an area that topographically appears to contribute to all the water that passes through a specified cross section of a stream. Okay. Now, for a stream in case of a river, or if you have a lake, then the lake is that particular specific point where you are measuring the volume. For groundwater, wherever you are having a pump or wherever you are having a some kind of outflow as in the form of a spring, you can take that point as a point of intersection. Okay. So, therefore, whatever is topographically contributes to that point is our catchment area or is our watershed area. Now, how do we delineate this? How do we know that what proportion of land falls into a particular catchment or does not fall into a particular catchment? Okay. This surface area, okay, that delimits this boundary, okay, is called a divide. Okay. It is given this term called divide. And how do we know, like so this is done by following the contour line. So, how do we do it topographically? So, in geography, if you have taken a geography class before, that in land surveys, when people are doing land surveys, they make maps, and while making maps we measure the elevation. Okay. The elevation is measured, and points having the same elevation, they are joined, and that particular line is called a contour line. So, when you are preparing a map, you will very commonly see this kind of map. Okay. So, this is a contour line map, and as you can see that there are numbers mentioned here, and those numbers are meters above the sea level. So, of course, I think you all must be knowing that water flows from high slope to lower slope, that is from a high altitude to a lower altitude. So, naturally water, the water that gets accumulated is flowing in a valley. So, there must be a lower valley, and there has to be slopes all across the valley, as you can see in this particular picture here, this particular picture. So, you can see that the river is flowing like this, okay, and this is the valley. So, this is the valley and this is the hill slopes, right. This is the hill slope that is contributing water towards this river channel, and these kind of delineations is done based on the high rises. So, suppose here is a range, okay. So, range means a upland, some kind of higher hill form, or some kind of thrusted sheet is there, or plateau is there, or it can be form of small hills, or it can be mountain ranges or things like that. So, it can, so basically thing is that there is a range, or that is the topmost point in that particular topographical area, and that is the end point of your divide. Okay. So, this is basically your divide, right. So, this is your, this is where the elevation is. So, where the range will be, by range I mean a hill range, a hill slope range, a mountain range, or it can be a plateau, or some kind of thrusted up, up thrusted area that cuts off, and again from that up thrusted area there will again be another valley. So, you will have you can have simultaneously separate valleys, or you can have so there will, in mountain ranges, if you have travelled, you will see there will always be valleys in between two ranges, okay, and the rivers will be flowing in those valleys. Okay. How will it occur in terms of aquifers? Aquifer is again, it is subsurface. So, how the topography is varying in the subsurface, and the water will be flowing based on the slope of the bedrock, and as well as there will be pressure gradients created, right. So, due to these two differences there will be groundwater flow, and in lakes what will happen is, lake is a small kind of very small basin. If the basin is very big, it can bigger very big lake, it can be a small lake, a small pond. So, the shape and size of lakes can be extremely variable. So, basically a small depression is created and all the water gets accumulated in that kind of depression. So, for that also, instead of instead of a discharge weir here, so instead of a dam or something here, you will just have a depression, a big depression, and all the water comes and accumulates in that kind of depression. And in olden days, this used to be done using manual methods, that is by doing land surveys and all that. Now, a lot of satellites is there, and it is extremely easily done using digital delineation. So, elevation, that is digital elevation models are there, and if you try to find out for any area, you go and try and download the DEM file, you can easily see the slopes, and you can be able to delineate this basin boundary extremely usefully. Now, this watershed understanding next helps us to understand the regional water balance. Now, water is an extremely important resource. Now, there is no question about it after the first two lectures, I hope. So, when we are talking about a resource, we have to first gauge how much of that resource is available or not. Okay. So, when we are doing any kind of intervention, before that we need to find out how much water is flowing, how much water will be stored, how much water is coming as runoff, how much water is coming from the groundwater, how much water is coming via rainfall. So, all these different parameters a particular hydrologist will be able to calculate. Okay. Now, let us break down these different small components in a catchment. You can see in this small image, this is a small valley. So, this valley, the regional water balance will provide the first hand characterization of the region's water potential. This is what is called the region's water potential. That means how much water is available for use. Okay. And of course, it is following the mass conservation law. Okay. So, there is a basic conservation equation, that is the first equation, and that is given by I minus O is equal to delta S. Okay. What is this I? This I is input, right. This I is input, O is output. Okay. So, this is input, that is output, and the difference between input and output is my storage. So, delta storage is my storage. Now, if I break this down further, my input will be broken down into P plus GWIN. What is P? P is for precipitation, that is in most of the catchments it will be in the form of rain, and in certain mountain catchments and catchments in the colder regions, it can also be in the form of snow melt water or ice melt water. So, that is my input, whatever is coming in the form of precipitation, plus sometimes groundwater will also come and flow into the river, because for all groundwater, whenever they are meeting and there is a slope difference, they will be seen to be flowing out as in the form of a spring, and they can also go under the under the subsurface they can flow. So, it can be you can see it on the surface, or you may not see it in the surface, but some contribution of groundwater is always there through the seepage. Of course, the amount varies from place to place depending on how the aquifer is positioned, how the river channel is positioned. Okay. So, depending on that, rivers sometimes have too much of groundwater, rivers sometimes have too less of a groundwater, but groundwater is generally found to be contributing to the network, and that is why we have this groundwater input. And subtracting from this input is Q plus ET plus GW output. What is Q? Q is discharge. Okay. So, discharge is the from a particular location. So, from here if I calculate what is flowing out from this point, this is my Q value. Okay. This is the volume of water that is flowing from this point, okay, per second or per hour or per day, something like that. So, it will be mostly reported in terms of meter cube per second. Okay. So, that is my discharge, that is my river discharge. Then groundwater, sometimes it so happens that there is a head difference between the aquifer and the river, that sometimes the river water can also flow into or seep into the groundwater aquifer. So, then groundwater becomes a negative, it is taken in the negative component. So, whatever is seeping back into the aquifer, that is my groundwater out. And ET loss, ET is the loss due to evapotranspiration effect. So, of course, there is evaporation happening, direct evaporation, or whatever is happening via the plants are taking up water from the soil moisture, and across, this is a catchment analysis, right. So, whatever is precipitation is happening, it is going out in the form of evapotranspiration, a great significant part is going out as a evapotranspiration. So, that is my evapotranspiration factor. And delta S, so whatever is the balance, that means input minus my output is my storage, and this is a very important thing to understand. So, it can be stored in the form of soil moisture, it can be stored in the form of groundwater in the aquifers and biological water, and mostly the water potential is found in denoted in terms of groundwater storage. So, how much is remaining back in the catchment, because once this discharge goes out of this boundary, we are no longer considering it in this catchment, or say suppose this is meeting the ocean here, okay, then in no way we can use that water any further. So, therefore, how much is getting stored inside the catchment, that is a very important parameter to understand the water potential of that area. Okay. Now, mu, this is a term and it is a long term average of any of the above quantities. So, I am not going into the details of how the regional water balance is subdivided and subcalculated, and there can be multiple ways in a hydrologist can calculate this, and this is the, I think, the most simplest representation of how we calculate the water balance in a particular locality. And finally, we come to this equation that is very important when we are talking about fluxes, okay, and that is runoff, that is denoted in the form of RO, is equal to Q plus groundwater out, and this particular equation is my flux. So, when I am talking about fluxes, how much flux of nutrients is happening, how much flux of contaminants is happening, this is what I am going to calculate, that is how much runoff is going out from as surface flow. So, that is stream flow, that is Q, and also in the form of groundwater. And particularly this is important because I am talking about aquatic geochemistry, this becomes a very important parameter. And this runoff is this runoff is the maximum rate at which water becomes available for our use. Okay. So, the groundwater output that we are taking out, that one, and the discharge that is happening. Okay. So, the stream discharge that is available for use, this is what is available to us for our usage. So, this again, as I said, is extremely useful for determination of the water potential of any area. Now, again a very simple description I will give you of this particular thing called hydrograph. It is extremely important to understand. Now, we have shown I have shown you this particular what is called image, where there is precipitation falling, evapotranspiration losses happening, groundwater is coming inside, there is storage and there is a discharge. Now, we will talk about a little bit more about this quantity, that is the discharge. Now, when we plot this particular discharge across time, we get something called the hydrograph. So, on this y axis we have discharge and on the x axis we have time, right, and how discharge varies across time, that is called the hydrograph. Now, here, so how does a hydrograph generally looks like? So, hydrograph, if I again just simply plot, the first basic plot will be like this. Okay. So, this is a simple hydrograph. And now, I will show you the basic small components of it. So, the first thing that is there, as you can see here, this line, this is the base flow. Okay. What is the base flow? That the base flow is the flow that is maintained during the low stage season or the dry season. So, in perennial rivers, this is called the base flow. Of course, there are two types of rivers. One is the perennial rivers and one is the seasonal one. One is the seasonal rivers, right. Perennial rivers mean that they are always flowing. At no time of the year you will find them to be dry. Seasonal ones, mostly they will flow with water during the monsoon season. Okay, so, this is very common in specifically in the Indian subcontinent, where we have stark in contrast in the weather, where the summer seasons will be extremely hot, so much so that the rivers will be drying up, and at other times there will be a lot of rainfall during the monsoon and therefore, the rivers will be flowing. So, there will be seasonal rivers. In that kind of rivers, this hydrograph will be very it will go down from the bottom, that means there is no water at all, or sometimes in perennial rivers there is always a maintenance of some discharge. So, this much discharge will always be there in the river. So, this is what is called as the base flow. That means, when it is dry, this value, this amount of flow is maintained. Okay. Now comes rainfall, and rainfall you can see it is plotted in this particular axis, and you can see slowly the rainfall values are increasing, day 1, day 2, day 3, day 4, 5, like this the rainfall is happening, and the frequency shows that it is a rainy season. So, this is monsoon, is if you talk in India, it will be called a monsoon season. Now, if rainfall is increasing, then you can slowly see the rising limb. Okay. So, this is the rising limb that is happening. Okay. And this is the time lag. So, this is the point of highest rainfall. So, this is the point of highest rainfall, and this is the time to peak. So, it will peak, it will not peak immediately, alright. So, your rainfall is happening on this particular day and your peak is happening on this particular day. We generally do not see such events. This can only happen if it has been raining for a significant amount of time, such that there is a flood event. So, the soil can no longer infiltrate the water. Most of the water that is coming from precipitation will flow as overland flow, and if it is raining extremely hard, that means there is an extreme amount of rainfall. This extremely high we are going to see an immediate peak. So, this generally happens when there is no infiltration happening, but otherwise we will see this rising limb, and this particular time period, the gap, okay, from the highest amount of rainfall to the highest amount of highest to the time that it takes to peak the discharge is called the lag time. Now, lag time is dependent on many factors. It depends on the vegetation, it depends on the the land cover, the land use, and how much water is being lost by evapotranspiration, and several other parameters are there. Then after peaking, it starts slowly decreasing. So, this is called the falling limb or the recession limb. Okay. And it may so happen that it may come down, okay, absolutely, and again be close to the base flow. Now, base flow, in the meanwhile what happens? Base flow, if there is a recharge to the groundwater, then it can also start contributing more. Okay. So, the more once the aquifer gets full, the groundwater component can also start take this kind of curve, that means it is increasing, or it may remain stable. That means, if it is deep groundwater and that it is not getting recharged immediately with this season's rainfall, then it will remain stable. So, there can either be a stable base flow or it can be slightly rising base flow, and again it goes down and becomes stable. Okay. So, both category of base flow can be there, and this base flow is always need not be always groundwater. Okay. There can always be any other supply source, maybe there is some lake water coming in, or maybe some anything that is supplying water, that is maintaining the river flow during the low flow stage, okay, during the dry season, that is whenever it is not raining. Now, having said that, now as you can understand, the hydrograph depends on how much rainfall is happening on that particular area, right. So, for a river like for a place where there is a single rainfall rainy season. So, this is my rainy season, say this is my rainy season. Okay. So, this is my monsoon time. So, the rivers is rising, and after the rainy season, that is called the post monsoon. Okay. So, the post monsoon, a few months, maybe 2 months or 3 months, depending on where you are staying. So, there it is post monsoon where you will see the mostly of the falling limb, and after that it will again start the winter, and generally it is the dry season, okay, followed by again the summer dry season and again the pre monsoon, and that starts, and therefore this rising limb and all that when that starts. So, in places where you have continuously high rainfall or where you have two two distinct rainfall events happening, then you can either have two curves as well. Okay. So, for rivers, some rivers you can always see that during some period of time this is raining very heavily, again it falls for a few days there is a lack of rainfall. So, there is a recession, again after a month or so or a 2 month or so again there will be high rainfall and it will start the discharge will start again going very high and all. So, these kind of hydrographs vary from each river depending on how the rainfall seasons are varying at that particular location. Now, why is it so important in terms of aquatic geochemistry? Of course, it is extremely important, as you may already understand, that water is not flowing with only water, okay, like the water is not alone. When rainfall is happening, a lot of processes are happening, a lot of interactions are happening with the soil, with the plants, there is uptake, there is release of materials, there is weathering, there is erosion, and then all of that water, the final solutes is getting released into the network, the stream network. So, hydrograph when it is getting more rain, when it is getting more time for interactions, all this controls the final river chemistry, and this can be more explained in terms of small catchments. So, in small catchments we can actually use tracers to see how the water is interacting at different locations across the gradients, how it is interacting, how in the how much water is going in, how much water is going into the plants, how much recycling of elements is happening in the small micro scales, and then groundwater that is coming in to this network, and there is this concept of transit time in controlling the solute concentration during the transport. So, when the river is flowing, that is it is gradually increasing its volume, right. When it is starting it has lower volume, it is gradually increasing because the discharge also increases. When there is a slope, that discharge also increases, right. So, this kind of movement is happening. So, here again it is starting less, again its volume is increasing as it is moving down the slope. Now, when you are seeing a rainfall event, a precipitation event, which water is flowing, which water is coming out and joining the river channel, that controls the chemistry a lot, right. So, there are different cases, this is a different cases, and you can find this extremely thoughtful paper by Professor C. Harman, and that was published in 2015 in Water Resources Research Journal. If you are interested in looking into more details about transit time and its control in the distribution of solutes in river channels, you please go and have a look, read this paper. And in a gist what I can say is that if you are having a particular event and you are pushing water into the system, this particular axis, this colorful graph shows the water age. Okay. So, this is basically the newest water, the red is the most new water, new event water, and blue is the most old water, right. So, which water is getting flushed, okay, what kind of distribution is it? So, if the proportion of new event water and the proportion of old event water is almost the same, then we call it the uniform distribution, that as soon as it is raining, the new event water is also getting discharged, the old event water is also getting discharged. What is old event, new event? Events are separate rainfall events. So, today it rained, maybe after a few days it is again raining. Now, the rainfall that is getting stored in the basin, that is getting few days time for interaction. So, that may have some more solutes. The new event water, they may have more rainfall solutes, rainfall related solutes. So, such differences between the different events water. So, this is a uniform distribution, or what is happening, you are supplying more water, the new event water is getting stored and the old event water is getting released. Okay. So, this is called a direct delta distribution, that is my only old water is getting released into the system. Or this another type of distribution, that is called the gamma distribution, and here we are seeing that in certain cases new event water that is falling, that is a maximum contributing to the stream flow, while that is which is the most oldest one, that is contributing the least. Okay. So, you can see the differences in contribution between the different aged waters. So, this controls a lot on the aquatic chemistry of that particular system. And when we are talking in terms of particular contaminants, this can become a extremely important parameter to understand and to quantify, and how it is how its distribution is to constrain that parameter. So, with this I come to the end of this lecture, and in the next lecture we will talk about sampling and how to collect samples in different types of aquatic environments and in details about those techniques. So, thank you. See you in the next lecture.